So we are going to discuss about lecture 4, starting with 4a. In this set of slides, we are going to discuss a very important concept, which is called recombination and diffusion. These are the two important concepts. And recombination, the carrier lifetime is related with recombination. So sometimes we refer to this resistance, resistivity, conductivity, conductance, etc. Those everything means same thing. Depending on the condition and the case that we want to discuss, we use the equation for conductivity, resistivity, resistance, conductance, etc. Here, so in this case, we will use one of the form of those equation, that is conductivity. Conductivity is given by Qn mu. We talked about mobility already, and velocity, dependence on velocity, the dependence on the velocity of the mobility. Dependence on velocity of mobility. Now we will discuss about. We'll go back to our initial discussion about the carrier concentration, how it affects the conductivity, and in turns resistivity and etc. Okay. Alright, someone is still trying to join the meeting, so let me do that. Alright, so let's see how the carrier lifetime affects the conductivity and in turns affects the resistivity and resistance. As I mentioned earlier, we are going to talk about two most important concepts. One is the recombination, another one is carrier concentration or diffusion. The primary equation for all this concept is this one. Okay. So let us focus on this one and describe each of the component. Nt means carrier concentration at any time t. So carrier concentration can be a function of time, and we will see how and why it will be a function of time. But for the time being, it can be a function of time. Okay, and dnt divided by dt represents the change of carrier concentration over time. Okay, so the change of carrier concentration over time is equal to generation, that is the uh, thermal generation or electron hole pair generation. It can be thermal generation, it can be optically generated, it can be we can generate EHP by applying potential, we can or electric voltage, and so on. So any kind of energy, we can use any kind of energy to generate electron hole pair. Now, as we know that when we apply energy after certain time, remember I use that term time. When we apply energy after some certain time, the number of energy input or the amount of energy input will become equals to the amount of energy output. I think we discussed this concept in the morning, that after certain time, when the temperature or energy state becomes equilibrium, amount of energy input will become amount of energy output, otherwise temperature will keep increasing. So so in order to maintain that equilibrium, or in order to maintain that certain condition, the carrier must recombine. Okay, otherwise it will, if the carriers remain in the high energy state, the temperature will keep increasing. So after recombination, the carrier will release the energy, and the object will dissipate that energy. As a result, the temperature will become a constant number, either 30 degree, 40 degree, whatever there is, depending on how much energy we're applying as an input. So in this, in order to describe this equation, I use that term time, uh, several instances. So that means that the carrier concentration can be a function of time. How? Initially, we can generate EHP due to external heat, light, or electric potential. After we generate that generate EHP, uh, because there are extra carrier, those carrier will try to recombine by releasing energy. So this sequence of events will happen at different time. First, we have to apply energy, then there will be generation. So I'm using all the time parameters. First is a time concept, then is a time concept. Okay. So first we have to apply energy, then there will be generation, then because of extra carrier or excess carrier that we call technically appropriate term, excess carrier. Because of excess carrier, there will be some recombination. Once the recombination happens, then the system will reach at a equilibrium point. Equilibrium point means if there are multiple uh, action or events going on, one of the event will cancel another event. And we have explained several examples of that particular process, that one of the parameter or component is equal and opposite to another parameter or component. When it happens, we call this equilibrium condition. So this is the fundamental equation for any for recombination, and also we will see we can use this same equation for diffusion also. So first talk about recombination. We are going to talk about recombination using this basic equation. This equation is very simple. If I consider my salary as time dependent parameter, first of all I get my salary at the beginning of the month, then I expend all my money during the month. So during is another time parameter, is a function of time. When I get my salary, initially I spend a lot, okay, and to repay all my loans, because I have to borrow a lot of money to maintain my life standard, so I have to repay all my loans. So that's the initial expense. Then after with the rest of the money, I buy some food, buy clothes, buy other stuffs over the month, which is a function of time. Okay, I hope that makes sense. All right, and so initially when I get my salary, the my bank account will go up, jump up, and over time, over the month, my bank account will slowly decline, or not slowly, very fast in most of the cases. So before the month ends, my bank account becomes zero again. And actually, I can show you some of the examples. I don't know. Maybe in the next class, I can show you the text message I get from my bank, and at the end of the month, how much is left. That you will be uh, that will be something to show you. And anyway, since we don't have much time, let me move on. Okay. So using that expression, once we have, suppose at t equal to 0, we apply some energy, and as a result of that, some of the excess electron hole and pair will be generated, and that at t equal to 0 we have a delta n and delta p as excess uh, EHP, initial excess electron hole pair, and they are generated in pair. Okay, now over the time, as the time goes on, we cannot maintain this amount of excess carrier anymore, because just like my salary, I cannot maintain that amount anymore. Over the time it will decrease. So my bank account will be function of time. So similar to that, the excess carrier will be also a function of time. And we know this excess carrier is equal because they are created as pair, electron hole pair. I think I have a so we are going to use this notation. This is at t equal to 0, excess carrier at t equal to 0, and this notation we are going to use it as if I call it del n t as a function of time. That means it's the excess carrier at any time t, and if we use t equal to 0, it will become delta n or something like that. So if we replace, so now if you notice, I don't have n0 here, I have nt. That means total carrier. Total carrier will be initial carrier n0 and excess carrier del nt. So we can replace it here. We can do the same for p. Is anyone trying to join? Okay. All right then. I think those who are interested to join already joined. Good. And we write the same form for the p, and it will give us this expression alpha r ni square. We know generation rate and recombination rate must be equal, so I'm not going to explain that. And if we do the math, alpha ni square minus alpha r n0 p0 will be cancelled out because I don't have it here, because we know ni square is equal to n0 times p0. So this is the term we have at the end. Now, since if we consider it as p-type material, p0 is much greater than n0, so p0 we can neglect n0 from this equation. Then this equation, and also del n is very small number. If we square it, it will become very negligible. So it's already written here. Now this equation will become this one. So we consider it as p-type material. However, we are getting the equation for n-type carrier or electron carrier. So when we use this equation, the final equation is for the minority carrier. The recombination equation, the final recombination equation is for minority carrier. We consider it as p-type, so it's a p0 is the majority, n0 is the minority. So the final equation, we can say the final equation is for the final recombination equation is for minority carrier, and it is expressed by majority carrier p0. Alright, we can solve this equation like this. So the minority carrier as a function of time is expressed by, obviously we have to use the initial condition at t equal to 0. Our excess carrier was delta n, so we have to write it as for the magnitude, and it is expressed in terms of majority carrier concentration. So in order to make this equation short, we can say tau n is equal to 1 by alpha r p0. Now this tau n is called the carrier lifetime of electron. Carrier lifetime of electron, or other term is called decay constant. We can derive the same equation for p-type. If we consider it as n-type material, then n-type electron will be majority, holes will be minority, and the final equation will be for minority carrier concentration as a function of time, which will be expressed by majority carrier concentration. So I don't know, I have that equation here, or if I don't have it, I believe you can derive it by yourself. This is very important slide, and it is a follow-up slide from this one. In this slide, I try to show you the effect of change of minority carrier. here, after I don't want to go through every single step. I think I have done it in the class, but the uh, conclusion is the percentage change of minority carrier is very large, is very larger than the percentage change of majority carrier. So although the electron hole pair EHP number is same, change of minority carrier is very large than change of majority carrier. So tell me why. Give me a practical example. So okay, so now it's your opinion because we are the majority here. Should I allow this person to join this meeting after 17 minutes? After repeated warning, repeated reminder, should I? Your vote.
Yes, sir. Consider for this time.
All right, so now you see how I'm interrupted every time I try to discuss an important issue. Okay, I will do that. What is it? Okay. Can someone give me a practical example why change of minority carrier is so significant? Okay. So if you don't have any example, let me do that. Uh, Suppose my name is Salman F. Rahman. Okay, and I'm not going to explain what I did for last 15 years or 16 years, but I have a lot of money. Maybe I can contribute to the next budget of Bangladesh. So if someone, some of you or one of you give me 10 taka, do I really care? I don't.
No, sir. Yes,
I
sir.
know, of course I don't. I can give you 10 lakh in return. But anyway, so since majority carrier, if you look at the number of the majority carrier, it's 10 to the power 15. So now, but however, number of minority carrier is only 10 to the power 10. So if I add little bit with P0, it does not really make any difference because it's already very high. But if I give 10 taka to who is really needy, right? Who didn't have lunch today. If I give 10 taka to him or her, he or she will be very delighted. Okay, so that's why. So it depends the how much do you have right now. Okay, so currently we have lots of holes, but very few electrons. So if you make any change in the hole or the majority carrier, it really doesn't matter. Only 10% for this example. But since we don't have much electrons, so small change in electron concentration will make a large difference. So that's our practical example. Okay. Now I always mention that the equation Ni square equal to N0 P0 is very important. Okay. Why is that? Here we have Ni given, the value for Ni is given, also the acceptor is given, and we are considering 100% ionization, so holes will become will be equal to 10 to the power 15 acceptor numbers. Now how can I calculate the N0? So here we have P0 given, Ni given, we don't know N0 yet, so we can calculate Ni square is equal to P0 N0, and we can calculate N0 equals to Ni square divided by P0. So that's why that equation is so important. So you may have to use that equation for many times. I mean, if not for this exam, for rest of your life, you are going to use it regularly. Anyway, so without going through the detail, every single detail, we understand that change in majority carrier is very small. Change in minority carrier will be very large. So since the change of minority carrier is very large, the change of resistance will happen due to change of minority carrier. Okay. But the resistance will change slightly, but very small fraction due to majority carrier. Alright, so this is the summary from this slide. Stop me anytime if you have any question. Okay, we are in this situation because you have not asked me any question during this semester. That's why I have to spend 3 hours in the morning, now 2 more hours, who knows how long in total, and tomorrow again. So that's why we are in this situation, because you have not asked me any question during the entire semester. Okay, raise your hand. Okay, Muntaha Majid Chaudhary.
Sir, I had a question from the previous slide. Sorry.
Okay, okay.
Uh, could you please explain why N0 equals to Ni over here? Because P0 is much greater than Ni, right? So shouldn't N0 be smaller?
Of course, N0 is smaller. N0 is this one. Oh, I see. I understand your point. So N0 is very small. If I do the math, so let me do the math here. Oh, you can see my calculator. How can you see? Okay, I can see my calculator. Two screens, three screens. Okay. Or anyway, yes, good question. So let me try to explain that. So on the left hand side, you can lower your hand. I mean, yeah. How do I say hand? Raise your hand, but lower your hand. Okay. Um, N0 times P0 equal to Ni. I will try to make the font larger. Let me. How do I do that? Font. I really don't like this new version of Notepad. It's very annoying. I mean, I don't like Windows 11 at all. Where is it? Where is my Notepad? Oh, here it is. And if you close something, it doesn't really close. It saves your whatever you have written last time. But anyway, so this is our equation. And you are absolutely right. Ni will be equal to 1.5 E10, and P0 is equal to, can someone tell me what is P0? I don't remember. 1
Sir, it's 10 to the power 15.
10 to 1 E15. Okay, so N0 should be equal to Ni divided by P0. Can someone tell me what would be the value for that?
Sir, 2.25 E5.
2.25 E5. Okay. Now, if we go back to our lecture, as you can see, P0 is equal to Na times Ni, not times, plus Ni. Now, similarly, we can write N0 equal to, we do not have Nd, right? What do we have? We will have uh,
Ni.
right, right. Let me before I do that, N0 we can write N0 as, because from that's the equation says, right? So that is from this equation, plus we also have electron hole pair. Okay, Now if I write put down the equation, all the values here, so 2.25 e to the power 5 plus, does everyone understand why I wrote ni here?
No, sir. Won't that
Okay,
increase the value?
okay, all right. So total number of carrier is this, and total number of electron is this. Okay, does it make sense now?
Oh, yes, sir.
Okay, so it will be actually n0. It should go like this. So what is ni? 1.5 e 10. Okay, so this is me and this is Salman and Rahman. Okay, we do not even compare. This is 10 to the power 10, this is 10 to the power 5. Okay, so it's a million times greater than my bank balance, or okay, obviously that's true. So now if I want to write the total value, we can write it as 1.5 e to the power 10, almost equal, right? Like this, almost equal. Make sense now?
Yes, sir. Thank you.
Okay. So that is why number of electron is, obviously, if you want to write the exact relationship, it will be almost equal to ni, but you know, million times larger, so it doesn't really make that difference. Okay, anyway, so I think that makes sense for everyone. But if you still have any question, let me know. Okay, let's move on to the next slide. So this is diffusion process. The summary of this slide is that if we have carrier concentration, that carrier concentration can go uh, in a random direct will diffuse in random direction. That means that a probability of going to probability of diffusing to any particular direction will be equal. However, the direction may be opposite. So 50% of the carrier will, or not the carrier, object or particle will move towards right. So when I say right, that also includes right, upright, like northeast, northwest, etc. So whatever it is, on the right side of this dotted lines. So if even if it moves this way, it will be on the right side. Okay, so that's what I meant by right side. We can make it even smaller sections. If I have another dotted line horizontally here, so this section will be 1/4, this section will be 1/4, 1/4, and 1/4. No matter how we divide it, the total the summation will be 1 in total. However, in order to keep things simple, I just have a vertical line, and I consider it right side or left side. So right side, we have only two sides, so there must be equal probability. So that means there will be half and half. Hopefully that makes sense. Okay, next slide is so I think some of you are confused about this diffusion process and the recombination. How can we combine or combine recombination? It may confuse you. How can we put diffusion and recombination together? So in order to do that, this is the first step, and it may be written here in detail, but in summary, the condition for this slide or this analysis is that there is no recombination. Two things actually. We are going to apply a short pulse. That means we are going to apply the pulse at t equal to 0 only. Then there will be no external energy. So that's the definition of short pulse. I think you know that already. So we are going to apply external energy at t equal to t equal to 0 only. Then that energy will be removed. If you consider it, I don't know how many of you have done Signals and systems. Everyone has done signals and systems. Most likely 341 or something like that. I have no idea. Or 241. Okay, if you are not done, that's fine. No worry about that. Um, anyway, in short, will have a very small pulse, a small period of pulse that will be applied at t equal to 0, and then there will be no pulse. Okay, so let me try to show you what I means by short pulse. So this kind of function is called short pulse. It is applied only at a certain time, and before that no signal, after that no signal. Okay. So this is called a short pulse. Ideally it is applied in only one dimension. Okay, now you can see someone is trying to get in. What is your vote? Should I allow? And it's already 3:33 after repeated reminder. So here you'll be the judge. I'm not going to take all the blame if I don't allow anyone to join. You have to tell me what should I do?
Well, since
Yes,
tomorrow is our exam, so I think you should consider it.
I should consider it. Okay, so
Yes, sir.
it's not on me, it's on you. Whoever you are allowing him to join this session. But should we continue to do it next time?
I think no, sir.
Good. Okay, he already left. Maybe he heard me. Anyway, so we decided to allow him, but he decided not to join anyway. All right. Okay, but we came to a conclusion that we should not allow this thing to happen, interrupt our discussion, because we don't have much time, but still uh, not everyone on the same page. Anyway, so this is called short pulse. So if we think about this way, it's a short pulse. We are going to apply it at t equal to 0 only. So you can see this is the short pulse. You see this very narrow and long signal, very short, very narrow, but very high. The height is very is a very the height is very great, long, um, or the magnitude is very high. Other way to say. So this is our short pulse. Okay, then there is no pulse. There is no external signal. Okay, keep that in mind. If we do that, initially there will be high concentration of carrier, but it will be very short, as I just showed you. The pulse will be very short, magnitude is very high. Now, now we have very high concentration, and there after that we are removing the energy, so no more EHP. But however, because of this initial EHP, the concentration will be very high here. Then that means there will be diffusion. No concentration here, no concentration here, only concentration here. Let me bring that signal again. No concentration here, no concentration, only at this point. Then there will be diffusion. So the diffusion will happen to the left or to the right.
Sir,
So
both
in both
both
directions.
sides.
Right, because the probability is equal, so it will diffuse on both directions. And as the time goes by, it will continue to diffuse. Okay, because after T1 we have concentration only here, no concentration here. So that means difference in concentration, then it will continue to diffuse as long it will continue to diffuse as long as there is a difference in concentration. It will only stop if the concentration becomes equal everywhere. Okay.
Sir, can you kindly explain what X represents here?
X is the distance,
Okay, sir.
because if you want to move somewhere, you must have some space. Make sense?
Yes, sir.
Okay, so let me show you. Of course, that's what I said. Huh? To keep. Okay, so I think you are very smart. So just to keep things simple, you do not understand things, and if I want to explain and build the case step by step, you become anxious. So let me finish first. And it also says that you didn't go through this slide. You are waiting for me to explain it one more time. So this is our, I'm trying to build up our story. Okay, we have two things. One is diffusion, one is recombination. First, just to keep things simple, I ignored recombination just so that I can explain diffusion. Make sense, smart guy? Okay, good. All right, so let me show you why there will be no more diffusion if we have equal concentration. I don't know I can finish it today or not. Okay, so again, now I don't know which one is appropriate. Maybe this one. Okay, here we have a queue at the bank. Okay. So you can see one person, two, three, four, five, six, seven. Now, if this person looks in front of him, there is someone. If he looks at the back, there is someone. Can this person move at the front to the front, or can this person move forward or backward?
No, sir.
No, sir.
Okay, why not? Because we have one person, one person, one person, one person, equal concentration. So when we have equal concentration, we cannot move anywhere. Okay, okay. This police or security guard can see one person in front of him, but there is no person behind him. Can he move?
Yes, sir. Move
Yes, sir.
behind.
Okay, which direction? Behind, right? Because if he wants to move forward, there is equal concentration, cannot move. But behind him is zero concentration, so he can, there is a difference in concentration, so he can move behind. So now you understand why everyone says that I am a genius. Okay, now we understand why why the diffusion will continue until there is a difference in concentration. Okay, is everyone clear with the diffusion process?
Yes, sir.
Oh, good. Now we are going to continue our discussion with diffusion. So derive some mathematical formulas. Suppose we have this kind of distribution, and we took two sections, 1 and 2, like this, and since where is it? The concentration in section 1 is greater than concentration in section 2. So the amount of particle moved from 1 to 2, we can write it as n1 minus n2, because that's the difference of concentration. Okay. Again, if I go back to, oh no, I will stop. Anyway, I think you understand. The concentration, the flow of particle will depend on the difference of concentration, of course, and okay. And the two will come from equal probability, because half of the uh, concentration from section 1 can go to the 2, or half can move to the left. Same thing will happen for section 2 also. So if we combine them together, this is our particle flow, net particle flow. um, and since there is a flow, that means there will be velocity. Think a particle cannot flow from one location to another location with the speed of light. It doesn't happen instantly. Okay, so it will take some time. So the particles from section 1 will cross total distance, because if we I think I already described all the geometrical terms. If it moves from center of section 1 to center of section 2, then the total distance covered will be L, and the total time will take t. So those are our, in order to express the velocity, we introduce those two terms. Length divided by time will be velocity. Where there is movement, there must be velocity, and velocity is equal to length by time. I think I already discussed in the class, so I'm not going to go through that because of time limitation. But if you have any question, you can stop me anytime. Is everyone okay with this equation?
Yes, sir.
Okay, good. Now, this is simple differential concept. I think you already know it. If we take that delta x, why you call it delta x? Because of the difference of length. Okay? The change of carrier concentration over the length of delta x. If we take the delta x tends to 0, to make it a derivative from the difference, we can write this equation. Why is it minus? Although we don't have any minus sign here, because we whoa, we consider everything initially, we assume everything positive, and then if the result comes negative, that means our initial assumption was incorrect, so we use that negative sign. So I can draw it here, but anyway, uh, uh, x plus delta x is greater than x, right? So if we assume positive, that means concentration at x plus delta x is greater than concentration at x. So since this is greater and this is smaller, this is our initial assumption. It is true or false, that is different thing, we can prove it later, but this is our initial assumption. And with that assumption, since we have it in this form, we need to add a negative sign here. Hope that makes sense. Now L square by 2t, we call it diffusion coefficient, that is given by dn, just to make this equation simple, nothing else. Okay. We can derive the same expression. So if we replace L square by 2t with dn, this is the form of the expression, we can derive the same expression for holes, and it would look like identical. Phi n, phi p, dn, dp, dn, dp. So both holes and electrons will have same form of equation, not the same equation, same form of equation for particle flow. Now, what is since there is a flow, there is a movement of particle, that means there will be current. So this is the total number of particles that will flow. So total number of particles means, if you recall the equation of nqv, okay, so if we nv, because we have concentration, we have velocity, we have concentration, we have velocity, so we already have n and q, n and v here. So in order to calculate the current, what do we need to do?
So multiply with Q, sir.
Right. So if you still have confusion, this is the equation for particle flow. We have n, we have L by T equal to V. That means we already have NV. And after doing all the math and applying for this particular scenario, this expression becomes minus dn by dx. But initially we started here. So this one includes n and v. That means that n and v is already here, because we derived this expression from here. So unit cannot be changed, right? The unit of this equation cannot be changed. The form may change, but the final unit will be same, particle per second or so. Hope that makes sense. Now we know equation of current is Q N V. we already know NV, we need to multiply it with the charge. So if it is electron, this charge will be negative Q, so minus negative Q dn by x, the sign will become positive. But for hole, so usually we take hole as positive sign, but the way the equation is derived, or the form of the initial equation, we have initially minus times plus Q. The final form, find the diffusion current. Equation for diffusion current for hole will have a negative sign at the beginning. And there is nothing we can do, it's just the way the equation is derived. We usually think holes as positive. So however, after derivation we can see the electron current will have positive sign, but the hole current will have negative sign. Okay, and I think I emphasized that in the class. So this is the only exception out of few. This is the only exception where the sign of the expression, not the charge is still positive, but the sign of this expression for hole is negative, but the sign for expression for electron current is positive. Electron diffusion current is positive. Okay, make sense? Any question? Okay, if there is no question, let's move on. So here is another complicated, or interesting, I should not say complicated, interesting concept. We see that when we have concentration difference, there is a flow of carrier, and flow of carrier will contribute flow of charge, and that means there will be flow of current, and that we call diffusion current. However, in this entire analysis, I have not applied any voltage. Ohm's law says V is equal to IR. So since I didn't apply any voltage, that means V equal to 0. So current must be 0. However, in this equation says current is not 0. And this equation comes from diffusion. Okay. Now if we look at this equation, the total current of electron and hole, it is combined with diffusion and drift. Okay. And we have already explained all the terms independently. So if we want to calculate the total current, we have to add drift current and diffusion current. So in this previous example, or the example that we are talking about, we already know there will be diffusion current. Why is there is diffusion current? Q is a universal constant, dN is also a constant for a material. Since there is a concentration difference, dN by dx, is it equal to 0 or not 0? If there is concentration difference, dN by dx is equal to 0 or not 0?
Not 0, sir.
Not 0. So in this term, three terms, everything is not 0. That means the total term or diffusion current is not 0. However, since I'm trying to relate, maybe I can write it. So sometimes visual explanation works better. Do you hear any noise in the background?
No, sir.
All right, good. You're a lucky one, because I think somewhere is construction going on, so I can hear the noise. Okay. So this is how I'm going to explain. This is so important. I will take as much time as I need to explain this. So how is it working? So while I'm writing, let me mute. So otherwise, you may be bothered by the noise that I'm hearing also. So, okay. But if you have any question, raise your hand, or let me know, raise your voice. Okay, I was disconnected for a short time. Let me, can you see my screen or do I need to share again? Okay, good, good. So what I was saying that you, whoever said that, made that comment is absolutely correct. We cannot break the rule of the nature. We have to follow it. We do not create the rule. The rule is already there. We just have to find it out. And all the scientists and engineers found out that there no voltage means no current. However, there is, we can see from the diffusion there will be current, but the final current cannot be must be zero. Internally there can be anything. Okay, internally there can be anything that can go on inside, but externally the current must be zero. So if internally something is happening, in order to cancel, in order to make external effect equal to zero, something is also inside happening inside that will cancel out the first effect, and the first effect was diffusion. If I want to make the total current equal to zero, we have to have another incident or event happening that is called, that we call drift current, and drift current must be equal and opposite to the diffusion current. If so, everything is tied with a particular condition. That condition is voltage is zero. If the voltage is zero, the drift current is equal and opposite of drift current. As a result, the total current is equal to zero. Okay, I think you are taking, you already took the snapshot. If you are not recording, you can take the snapshot so you can go through that concept later. Okay, I don't. Now I forgot why I wrote this thing. Because of I was disconnected and lost focus. So okay, now okay, now I remember, I guess. The reason I wanted to show you this equation and derive this, went through these steps, is because it says, this equation says that if the voltage is zero, so there are two things actually. First condition is concentration difference, because if we don't have concentration difference, the diffusion current is zero, right? Then we don't have to think about drift current because everything will be zero then. So the initial condition is concentration difference, and second condition is no voltage. So this, whatever I have written here, is valid only if there is concentration difference and there is no current, no voltage. Make sense? Because I used those two conditions to derive this equation. So if these two conditions are not true, then this equation is not true. So if item number 1 and item number 4, any of the items from 1 and 4 is not true, then number 6 is not also true. Do you understand this? Okay, good. So that's why if I change the condition, this equation will change also. So every equation is valid for certain conditions. You have to remember it. Not all the equations are valid for all the conditions. We don't have any universal equation for anything. Okay, I hope that makes sense. Now what does it say? That if there is concentration difference and if there is no voltage, then drift current will be equal and opposite of diffusion current. Okay, we established that fact. Now the question is, what is drift current? What is the equation of drift current? We have already derived the equation of diffusion current. What is the equation of drift current? From previous derivation and all the other analysis on explanation, the drift current is equal to N Q N Okay, so this is the expression for the drift current. Okay, all right, which is good. We just proved. Oh, okay, by the way, so here it is not equal to 0. That means drift current is not, diffusion current is not equal to 0. That means drift current is also not equal to 0. Q is universal constant. N is the number of carrier. It's also not equal to 0. Mu is the mobility, not equal to 0. Since the equation is not equal to 0, we know those are some constants. So we can write E. I don't know how to include proportionality constant, alpha A, no, A 2. How do I insert proportionality constant? Anyway, whatever. So is not equal to 0. Does it make sense? This statement. Q not 0. N not 0. Not 0. So there is only possibility that this equation will be 0 if E equal to 0. But this equation is not 0. So that means E cannot be 0. Make sense?
Yes, sir.
Good. So E, what does E means? E means electric field. Okay. So after all these steps, we proved that electric field cannot be 0. That means there is an electric field. Okay. How do we come to this conclusion? What are the initial conditions for this equation, for this derivation? Do we have any initial condition?
Yes, sir. No voltage source and have a concentration difference.
Right. If we have concentration difference, and also if we have if the voltage is 0, diffusion current not 0, that will make drift current not 0, and that will make electric field not 0. So if I can conclude that if there is concentration difference and if there is no voltage applied, there will be an electric field. Obviously we have to go through all the process and everything, but the conclusion is there will be electric field, but we did not apply any voltage. How do we get that electric field? That's another question. So that's why, although the applied voltage is what? Internal, right? Sorry, external. We apply voltage externally, but this electric field is not generated because voltage is 0. So that means this electric field is not generated externally. That means this electric field is already inside. That's why we call it built-in electric field. All right, so I think I was thinking about it, how can I explain it in a better way. So if I do this, and I would like you to structure your answers like this. So so this is one example how you answer it. So if I ask you a question, if there is any concentration difference and if there is no voltage applied, prove that there will be built-in electric field. So what you can do, you can structure your answers like this. So these first two are the condition or cause. Okay, the center part, step 3, 4 and 5 are called process. Using these initial conditions, we are going through a process and we will come up with the result from that process, and the result is there will be built-in electric field. Isn't it beautiful?
Yes, sir.
So So for any question, you can answer in this form, at least for this course. So most of your questions will be cause and the result, cause and effect. So you can structure your answers like causes, then explain the process, and then write down the results. Okay, so if you do it, it is easy for me to go through it, because otherwise I have to read really long sentences, and with my span of concentration, if I if a sentence is more than 8 words, I forget what I read at the beginning. When I am at the end of the sentence, I already forget what is at the beginning of the sentence. That's why it takes long time for me to check your answer scripts. Okay, but obviously I do not lapse. I score you fairly. If I forget anything, I read and read and read again and again every answer script, so I can give you fair score. Okay, so that's why I do not sacrifice any quality. It may take some time for me, I acknowledge that, but I'm always fair, and I do not sacrifice any quality anyway. But if you do it, it will be easy for me to go through it, and it will be easy for you to answer any questions. You don't have to write all these long sentences etc. But again, this is just personal preference. I prefer it this way. I don't know how you prefer it. But anyway, there are some benefits if you do it this way. But it is your choice, whatever you prefer, whatever method or whatever style you want to follow. That will be your choice. Anyway, any question? Okay, if not, let's move on. I think it's already 4:10, so we need to get this thing done as soon as possible. So now we understand the origin of built-in electric field. Okay, this slide is also very important. I'm expecting a question from this slide. So we have concentration, distribution, and also applied electric field. Remember, it is applied, not built-in. It is applied electric field. Okay. So if I follow the concentration gradient for electron, the particle will flow from left to right, and because of the electric field, electron will move in the opposite direction of electric field, just like this, and we can derive the current also. So for the current goes opposite direction of electron flow, so that's why it's this direction. For drift, same, current will go from opposite direction of the electron flow. Okay. For the holes, high concentration to low concentration, and same for electric field, same direction of the electric field, same direction of applied electric field, so that's why. And the current will follow similarly, same direction of diffusion particle flow, same direction of drift particle flow. Okay. All right, any question? All right, let's move on. These are all derivatives of whatever we discussed initially. So let's take a look at this one. Here we have the whole current, we have the whole concentration distribution, but no applied electric voltage. This electric field is built-in electric field. Okay, so no external voltage. So what will happen? Whole current will be zero. Drift current, diffusion current, summation of drift and diffusion will be equal to zero. Again, the diffusion for whole will be negative sign. That's the only exception. If we do the math and everything, so we can divide the entire equation with q, and q will cancel out because we have 0 here. If we divide the entire equation with dp, we will get if we divide entire equation with mu p, we will get pe minus d by mu dp by dx. Why do we need to do what is the importance of dividing it with mu p? We have this equation derived later. D by mu is equal to kt by q. So this is k is a universal constant, q is universal constant, T is room temperature, everything is constant on the right hand side. So we want to make everything constant, so that then we don't have to deal with the variables, which is a headache. Okay, so if we do that, we can come up with this expression, dp divided by mu p divided by px dp by dx. Okay, so this is the expression of electric field. Now what was the condition? Current is equal to 0. So in this slide, do we satisfy, where is my initial two conditions?
Yes, sir.
Okay, how? Because we have number one, carrier concentration difference, voltage equal to 0. I don't have it here explicitly, but current, that means current equal to 0. So we satisfy these two conditions. Now after satisfying these two conditions, if we derive the electric field, what do we call that electric field?
So built-in electric.
Right, built-in electric field. If we use this condition, concentration difference, current 0, concentration difference, I have dN by dx, but you can use it dP by dx, is the same. Concentration difference, current J equal to 0. If we satisfy these two equations, the electric field we get is called built-in electric field. Remember, this electric field is not generated by applied voltage, because we don't have applied voltage. We cannot generate that electric field from the applied voltage. So that means it is already inside the material. Because it's already inside, we call it built-in. Okay. Alright, I hope that makes sense. So now you can understand this slide is just a derivative what we already discussed earlier. Okay. All right. I hope all these notations will make sense for you. If not, let me know. Okay. And with the same condition, by applying the same condition, we can derive this famous equation. It is called Einstein's equation. If you go through that, you will see this is the equation we can come up with. Okay. Any question from this slide? All right. If not, let's move on. Okay. I cannot move on. I have to explain it. So we have this expression of Ex. We have the expression of Px. And how can we define the Px? Px is total carrier, total free electron, free holes as a function of time, a function of x. So we can write Px. When we call P0, that means same concentration everywhere. However, it is not same concentration everywhere. So that's why we cannot write P0. That's why we have to write Px. Okay. So if we replace the value of Px in this equation, you should get this expression. Okay. And after this, because no current means the Fermi level is constant. Do you remember? The condition is no current. Using that condition, we can write the Fermi level is constant. Now we have this expression, and rest are already written here in different steps. Any question? All right, I think you understand it. Most likely there will not be any question from this slide, but so that your knowledge is complete, I'm going to go through these steps one more time. considering those two conditions, concentration difference, external voltage equal to 0, considering those two conditions, we derived this equation for built-in electric potential. And also we know P can be written, or the total hole, number of hole can be written as Ni e to the power minus Ef minus Ei divided by Kt. If we replace this value of Px here and also the derivative here, we should be able to derive this form of equation. Now again going back to our original condition, which is current equal to 0, and if there is no current, from previous discussion we know that Fermi level will, the derivative of Fermi level must be equal to 0, so this part is 0. Then we will have only this part like this. Then rest are already provided here, all the steps are provided here. If you go through this step, you should be able to derive this equation. D by nu is equal to Kt by Q. Okay, this is pure mathematical derivation, nothing else. Of course, we have to apply some concept, and that concept is this. If the current equal to 0, Fermi level, derivative of Fermi level equal to 0. And as I mentioned, this is same variation. Here it is done with holes. Here it is done with electrons. Other than that, everything is identical. All right. Okay.
Yes, sir.
That concludes this set 4A. Let me try to finish 4B. We have 40 more minutes, and I have to change also. But anyway. Okay. At the beginning of the lecture 4A, I mentioned that we are going to discuss about two major items. One is concentration difference, another one, or concentration difference means diffusion. Another one is recombination. So we discussed that separately. Someone mentioned that why we ignored, what was that? Yeah, I think here or here, maybe someone, where we ignored recombination or diffusion. And you are absolutely right. You are absolutely right. We should not ignore. But in order to keep things simple, we discuss them separately. Now we are going to combine. So that is called superposition principle, right? Separate solution, then combine all the solutions. So in this set of slide 4B, we are going to combine diffusion and recombination, as the title says. Okay. Okay, so at the beginning the number of participants was 41. Now I can see 37. I think I bored some of you, at least 4 of you who already left. So those who are still in this call, hopefully I'm not making you bored. Okay, anyway, so in order to combine diffusion and recombination, we have to set up an experiment. In this experiment, we have a small cube with cross-section area A, and the distance is delta x, and the input current Jpx, output current Jpx plus delta x. Usually the current input must be equal to the current output, but in order to keep our discussion general, current input equal to current output is very specific, no other option. But we want to start with general concept, then we can apply special rules. So the amount of hole build up, or the rate of hole build up, will be equal to current in minus current out. Why is that? Because if the output current is not equal to input current, that means input current is greater than output current, that means sum of the holes can enter this volume but cannot exit this volume. That means they will build up, just like water tank. Give me a second. Again, I always try to provide visual example. So let's say I don't know which one is appropriate, but let's see. Maybe this one is appropriate. I don't know. I've never seen this one. Come on, quick. Okay, so here we have a water tank. There is input valve and output valve. Forget about this level. I don't even know what it is. So if the input is more than the output, that means the water will build up. It's a simple example. I just have to provide you that, show you. Anyway, so that's the concept of hole build-up because of current difference. However, just like that water tank, if we have a leakage, that means the build-up will be slow because we are leaking some of the water. And with the same concept, the leakage of water can be applied as recombination in a semiconductor system. So because of the current difference, hole is building up. However, because of the recombination, we are losing some hole. Just like because of the leakage in the water tank, we will lose some water. Just like that, because of recombination, we are going to lose some holes. So that means we have to subtract the recombination from the buildup. So the final buildup equation should look like this. And I have already explained why should we, Mr. Tamil, why should we use K, right? Because on the left hand side the unit is particle per time. So in order to, but the current equation is ampere per time. So in order to make it a particle, we have to divide it with Q, because J is equal to NQV. Do I have it here? No, J is equal to NQV. That's a charge, total charge. So in order to convert total charge to a total number of particles, we have to divide it with Q. And the rest of the items we already know that. Okay, so this is a difference equation. We can convert it to a differential equation, and just as previous one of the previous derivation, since we have JP, that means on the left hand side minus right hand side, we usually consider that right hand side is greater than left hand side, so we have it negative sign, so that's why we have to use a negative sign. So initially we are going to follow the positive slope convention. If it is not true, that result will become negative anyway. Alright, I hope that makes sense. So this is our final form of equation. This is for the holes and this is for electrons, same form of equation. Oh, by the way, for electron we have to divide it with negative Q, minus Q, right? So minus and minus will become plus. See, all the sign conventions are maintained. Okay, and from previous discussion, so this is just because we only have recombination here. In this equation you can see we have only recombination, and we have the equation for current. But what is the diffusion? So if we consider all the current is from diffusion, then we can write the equation of current in terms of diffusion. All right. Now we have an expression that combines diffusion and recombination together. Does it make sense? Isn't it beautiful? Okay. So I didn't get any answer of anything, any of the question. Does it make sense?
Yes, sir.
Is it beautiful?
Yes, sir.
You cannot answer that. Anyway, let's move on. Okay, so in this equation, using this experiment, and considering all the current as diffusion current, we came up with this expression where we combine diffusion and recombination together. So that's the beauty of this equation. Next, and obviously this is a very complex equation. It's a function of x, function of t. So that means partial differential equation. We don't like it. Or I don't know about you, but I don't like it for sure. So, and most of the people don't like it. So that's why they did lots of study, and they came up with this idea of steady state carrier injection. What is steady state? Steady state means no change with time. Steady state means no change with time. So in this equation, we see there is a term which is a function of time or derivative of time. That means it represents the change in time. But we say we don't want any change with time. If there is no change in time, what is the value of this left hand side of this equation?
Zero.
Right, because no change in time, that means this derivative will become 0. If that derivative becomes 0, we have only these two terms, and then we can divide the entire equation by dn or dp. So it will become anyway. Oh yeah, right. So for holes, if we divide this equation with dp, on the left hand side we will have delta square delta p or del p divided by delta x square is equal to, because if we take this one on the right hand side, minus will become plus del p divided by tau p, which is the carrier lifetime of holes, times and divided by dp. We can write the same equation, similar equation for electrons would look like this. Here we, in order to make it simple, we call dp times tau p as diffusion length, which is given by lp square. That means lp is equal to root over, or ln is equal to root over dn tau n. Lp will be equal to root over dp tau p. Okay, and this particular term is called diffusion length. That's all. Okay, so now again, these are all sequential. We have to go step by step. We have to go step by step. Initially we discussed about diffusion. We also discussed about recombination separately. Here we are going to combine them together with this experiment of input current, output current, and also recombination. So and later we consider all the current coming from diffusion. So that means we are combining diffusion current with recombination. So this equation combines diffusion and recombination. If you remember, we have not combined diffusion and recombination before this point. We talked about diffusion and recombination separately, never together. In this is the first time we're talking about diffusion and recombination together. Okay, all right, I hope that makes sense. And so first assumption, after building this equation, the first assumption was all the current coming from diffusion. So we can combine diffusion and recombination together. Second assumption, we want steady state, no change in time. No change in time, that means the time derivative will become 0. So here, and after doing all this math and everything, we come up with this equation where we combine diffusion with recombination. Tau is a recombination time constant, so we combine diffusion change with respect to x, that is called diffusion, right? Concentration gradient, concentration difference. Can we have concentration difference with respect to time? Concentration difference, is it a function of time or function of x?
X, sir.
Right. Okay, so that's what we have on the left hand side, and that means this part represents diffusion and tau represents recombination. So again, this equation combines diffusion and recombination together, but with a special case of steady state. This is the general equation where we have function of time, function of x. If we apply special case, that's why I mentioned initially, we will start with general case. Then we are going to apply some special condition. First special condition, all the current will come from diffusion. Second special condition, no change in time. So that will give us this expression, which combines diffusion and recombination together. Okay. All right, good. Now, since we have, is it partial differential equation or regular differential equation?
Partial difference.
Partial.
Wrong. Everyone is wrong. What is the definition of partial differential equation? Definition of partial differential equation is the
Sir, it is good.
right, if the dependent parameter is function of only one parameter, that is called regular differential equation. But if a dependent parameter is a function of more than one parameters, one variables, in this case more than one means x and t, that's why then we call it partial differential equation. Although the symbols looks like partial, but by definition this is a regular differential equation, because delta p is our dependent variable, is a function of x only, right? I hope that makes sense. All right, so since we have differential equation, we should be able to calculate the solution. The form of the solution. As you know, in differential equation, we try to identify the form first. What kind of differential equation it is, and this is a very standard and well-known form of differential equation. That is that the double derivative of dependent variable is a function of dependent variable itself. If we have this kind of equation, the solution is an exponential function. Since again we want to keep everything, we want to start with the general form. So this is our general form. It can go in minus x direction or it can go in plus x direction also. So we consider everything. Then we will apply our boundary condition and we'll see what happens. So here the term we should use is boundary condition. We should not use any final value or initial value, because final value and initial value represents function of time. Here we do not have function of time, it's only function of distance. So, for function of distance we call it boundary value. So one of the term is initial value, final value, that is applied for time. But if we want to apply the condition for geometric dimension, we call it boundary value. Okay, so if we use the boundary values, our a object must start at x0, right? If we want to calculate the distance of some point, the initial is what? 0. Distance 0, then we increase the distance. So an object is defined by between 0 and x. So we don't have that object before x, before 0, and we don't have object infinitely on the positive side. Okay, so since we do not have that object before on the left side of the 0, then the carrier cannot diffuse to the left side, right? Because there is no object. Suppose if we place suppose we have a aquarium, small water tank, and if we pour water on the one side, that water will move to the other side, but the water must stop at the wall, glass wall of the aquarium. It cannot cross that glass wall. So that means the water, we will have water on the one side diffused on the one side, but other side there will be no diffusion because of the high barrier of glass wall. Okay, I hope that makes sense. So that means our objective, our water tank or whatever you call it, is defined only greater than x equal to 0 region. Okay, so that means there should not be any diffusion on the left hand side. So if we say that, so delta, and also because there will be recombination, because of the recombination after certain distance, all the carriers will be, all the extra carrier will recombine, right? Because we are considering diffusion and recombine, remember. So there will be diffusion, the electrons or the carrier will try to move to the low concentration area, but when it is trying to go to the low concentration area, it will also have recombination. I think someone also already mentioned that what will happen if we have recombination during diffusion. It is possible, and that's the realistic case. So there will be diffusion, but while it will diffuse, there will be recombination also, and since there will be recombination, all the excess carrier will recombine after a long distance. Okay, so that's why delta, I guess this is called del P will be 0 at x equal to infinite. Okay. So if we replace that boundary condition here, that will force us to make C1 equal to 0. Okay. All right. My battery is very low right now after speaking 5 hours in total, but I will complete it before I die. I will complete this, finish this slides, but give me 1 second. Okay, I hope that it makes sense that after a long distance all the carriers will recombine, so that means our excess carrier will be 0 at x equal to infinite, and that will make C1 equal to 0. And as you know, if we apply a external energy at x equal to 0, at t equal to 0, there will be high magnitude of excess carrier, and we define that as del P. No, sorry, this one is del P, and this is the del P. So del P, come on, delta P is the value of del P at x equal to 0. Okay, so stay with me. I will go a little bit slow because otherwise my brain will not work on, already stop working. So in order to provide you the correct information, I will go slow. Okay, delta P is the value of del P at x equal to 0, and if we apply that boundary condition here, C1 is already 0, we will get del P as a function of x equal to delta P, which is the carrier concentration at x equal to 0, times e to the power minus x divided by LP. Okay, do you understand the derivation now? Okay, I think I'm the only one alive here. Is there anyone on the other side?
No, sir, it's clear now.
Okay, all right. Okay, again, remember what was our starting point? Our starting point was this experiment where we considered difference of input current and output current, and we also considered the recombination. So if I want to write those steps one more time, oh, here it is. Okay, if we do that, and the mathematical expression for this condition would be okay. So 1b describe the recombination, loss of carrier. That's why we have to subtract that amount. However, 1b requires little bit more description. 1b represents diffusion, and 1a represents diffusion, and 1b represents recombination. So I wrote diffusion here, but this is explained as current. Why is that? If the input current is not same as output current, does it mean there is a difference of concentration?
Sir.
Yes, sir.
Okay, why is that? Because I in will be equal to Q in divided by T, and output current will be equal to I out equal to Q out divided by T. Okay, T and T will be cancelled out. If I want to write the equation, I'm sorry, I'm too much detail oriented, and I cannot do anything otherwise. So that's why I have to go through all the steps. As I started, I need to finish it. This is my problem. Not equal to. Oh, okay. All right. So we can write okay. So T and T, we can cancel out T and T. So what does it say? Input charge is not same as output charge. That means, is there any difference?
Yes, sir.
If there is difference, are we going to have diffusion?
Yes, sir.
Okay. So that's why diffusion can be represented as difference of current, which from which we can derive that there will be difference of carrier concentration. That means there will be diffusion. See how beautiful this is. All right. Now 1b is recombination. We are going to lose some carriers because of recombination. So this is our initial assumption. Remember, we are going to do as cause then process. Okay. So what would be our process? The first step would be assume all current from diffusion, and that will help us to formulate the expression for Jp or Jn, whatever. So we know if all the current is from, if we neglect drift, all the current will come from diffusion, and if all the current comes from diffusion, we know the expression of the diffusion like this. So now we are ready to write the equation in terms of diffusion. So that's why that assumption is important. Wait a second. Okay. Now the second process would be steady state. And what we will get with the steady state, it will give us time derivative equal to 0, and that will help us to simplify the equation just like this. Now we will have, so what is our result? And recombination. Okay. And obviously you can get the equation from here. I'm not going to write it. I don't think I will be able to write it with notepad, all these symbols, but I think you understand that. And once we have the differential equation, we should be able to solve it applying boundary condition. Let me do it anyway. Okay, all right. So this is our final solution. You can see it's the same type of expression, exponential expression. The first is the magnitude at x equal to 0, and then distribution over x. If you remember the equation for recombination, we had the identical expression, but that was function of time instead of x, and that had magnitude at t equal to 0, then exponential function of t. If you don't remember, go back to the lecture slides and you should see. Okay, all right then. Any question from this slide?
Sir, can you please open the notebook, sir? We have to put the snapshots.
So
Thank you, sir.
okay. All right, so we did it for holes. Now we solve the equation for holes. We can solve the equation for okay. Now now we know the distribution of holes with respect to x. Okay, let's see. Again, going back to our equation of diffusion. This is the equation of diffusion. If you do you recall? If not, let me show you one more time. So equation of diffusion, q dn delta dn yada yada yada, like this. For the whole, it will be same form of equation, but again only exception is negative sign. in the current equation, in the equation for current, this is the only exception. The whole diffusion current has negative sign. All other components will have positive sign. Okay, anyway, so this is the form of the equation. We know the expression for px, p as a function of x, so we can put the p as a function of x here, right? Because we need to take the derivative. Okay, if you notice, this equation becomes this, p becomes delta p. Why is that? Can anyone tell me? The answer is in this slide already also. Okay, all right, it's already 4:50. I can hear my driver is here already. Anyway, but we have I guess 2 or 3 slides. We can, hopefully we'll be able to finish it on time. Can anyone tell me why this p becomes delta p? Okay. So this is why. The total whole is equal to doping concentration plus excess carrier. And excess carrier, how do we generate excess carrier? Light, heat, or any other external energy. We cannot change the P0 because P0 is permanent change, but light, heat are temporary change. Temporary change will be function of time and also function of space. So here you go. If I go back to this plot, you can see P0 is always constant. See, but the excess carrier is not always constant. It changes over x, and it also previously we also derived it is also a function of time. So excess carrier is always function of time and function of the distance. But if you consider a steady state, it is only function of x. Is P0 a DC value or AC value?
It's a DC.
DC in terms of as a function of x is a DC because x is changing but P0 is doesn't change. So if I take the derivative of P0, what would be the value result?
0.
0. So which part will be remaining?
Delta px.
Delta px. Okay, your volume is very low, but I can still hear it, barely hear it. So that's why we can take that derivative of constant out. We can only keep the component which is function of x. That's why p becomes delta p, because we eliminated dp0 by dx. That has no value for us. Make sense? Anybody?
Yes, sir, understand.
Okay, good. And also we are calculating diffusion current, and for the diffusion current we need concentration difference. But if we consider P0, is there any concentration difference for P0? Look, I'm speaking for 5 hours and I'm still going on. No one has any energy to reply a simple yes no question. That's unfortunate. Okay, anyway, if you want to participate, if not, that's fine. So since P0 is constant, there is no concentration difference, there will be no diffusion current for P0. So since we want to calculate the diffusion current and P0 has no diffusion current, so that's why there is another reason we can ignore P0. That's the analytical explanation, but mathematical explanation is since P0 is constant with x, the derivative will be 0. That's why we have only the term which is function of x. Okay, all right, so we have it now. We know the delta p. If we take the derivative with respect to x, it will become like this. And if you notice, the result is very interesting. In the result, we have again delta p e to the power minus x dp, xl divided by lp, which is identical to this expression. That means we can replace this part with q dp by lp times delta px. So what does it mean? It means that diffusion current is proportional to the excess carrier concentration. So again, the result means diffusion current at any x, diffusion current at any point x is a function of concentration, as a function of excess carrier concentration at x. Diffusion current at x is proportional to excess carrier concentration at x. This is a very important conclusion, and of course there may be a question from this particular results. Okay, since I don't know if anyone is out there, but doesn't matter, I will go on. I will stay as long as it need to be to complete this. Anyway, so I think we talked about this. This slide is not included in the midterm, so I will skip it. Again, this slide is not included in the midterm, so I will skip this. This is not included, not included, not included. Right, so we have last three slides. However, I can explain it from this slide anyway. But the other two slides are also included, but I'm not going to go through this because these are mathematical derivation. You can do it by yourself. Hopefully, not hopefully, I'm sure you can do it. That's why I'm not going to go through it, but I'm going to explain the basic concept. So when there is no external energy, no applied voltage and nothing, the only carrier we have is from the doping concentration. But as we have explained many times, if we apply external energy, there will be excess carrier, and the excess carrier can be function of distance and also function of time. However, in this particular example, we are considering steady state. So because we are considering steady state, excess carrier is not function of time anymore. Steady state means does not change with time. If it does not change with time, we cannot take the derivative, or derivative will be 0. So that's why we have only excess carrier function of x, because it is steady state. Right. When the carrier concentration is n0, it has specific Fermi level. But if we add more carrier, or call excess carrier, or generate excess carrier, then the total number of electron will change. And we know that number of electron is directly related with the Fermi level. If the number of electrons change, that means the Fermi level must change. Okay, so initial Fermi level, which represents n0, is EF. Now, because of excess carrier, if we change the total number of electrons, then the Fermi level will also change accordingly. And the new Fermi level, we call it quasi-Fermi level. Since the carrier concentration, since the excess carrier is a function of x, total number of free carrier will be function of x. Because the Fermi level is related to carrier, and carrier is a function of x, That means Fermi level, which we call quasi-Fermi level, will also be function of x. So that's the main concept. Now we can use this expression to derive different equations, just like this. Then we can do it, apply it for the total electron current. We can do it for whole electron current, just like this, the total electron current and the total hole current, and all the derivation are provided step by step. So you can apply this formula everywhere. You should be able to derive all this expression. Okay, so that concludes our discussion for 4b. Obviously, it's, I'm in a rush and I want to head out as soon as possible, but I'm not going to do it unless you tell me that someone tells me that you don't have any more question. I'm kind of bound by this spell that I have to complete this lectures and try to help you to understand all this concept. So do you have any question that whatever we discussed so far? If you have any question, I'm really happy to discuss those. But you have to let me know, otherwise I cannot read your mind. Okay, all right. Let me see, do we have our regular participants here? I can see most of the regular participants are here, but I don't hear them. Do you have any question? Anyone has any question?
No, sir.
No
Sir,
questions, sir.
how many questions will be there in the
Okay,
midterm exam?
that's interesting thing. So I cannot tell you that because I have not prepared the questions yet.
Sir.
But the time, there will be fixed time, obviously, 90 minutes, 1 hour and 30 minutes in total, and obviously I will set the questions according to the time. Okay, so you can complete everything within the time limit. Okay, I don't know yet, but there may be options. Maybe you have to answer 4 out of 5 or 3 out of 5 or whatever there is. I don't know yet. Okay, but no matter what, you should be able to answer everything within the given time. And the trick I showed you, if you follow it, you should be able to answer it very quickly. Use this format: cause, process, and then results. I don't have any diagram here, but if you need to draw any diagram, you should add that. I don't have any option to draw a diagram in this in the notepad, but in order to make a complete answer, if you need to add any diagram, add the diagram. But try to follow this format. I hope that will help you. At least try it once. If it doesn't help you, go back to your original style. You will not know whether it will work for you or not unless you try it once. Maybe try it at home. Anyway, so that I hope that answers your question. So I don't know exactly how many questions there will be, but most importantly, you should be able to answer all the questions within the given time. That's it. And there may be just maybe options that maybe 4 out of 5 or something like that. Anything else?
Yes, sir.
Okay, I am glad that we had this session. It was a long session, and so hopefully you learned something. If you learn something, those who are not present, try to help them. Do discussion, consultation. I mean, yes, of course you can do your consultation. It's not only my responsibility, your responsibility also. But and also, by the way, I'm going to post it in the Google Classroom. As I mentioned earlier, I will be available tomorrow from 9 to 5, or maybe 9 to 4:40, 9 to 4:45, because I need 15 minutes to go to the exam room and etc. etc. So anyway, 9 to 4:45 I will be available in my office. If you have any question, feel free to stop by. I cannot do online lecture tomorrow because some of you may have exams and etc. etc. So I'm available in person in my office between 9 to 4:45. So stop by if you want to, anytime you want. Okay, if there is no other question, I think we are done for today, and good luck with your exam.
Thank you,
Thank
sir.
you so much, sir.
Okay, all right, see you tomorrow.
Assalamu alaikum.
Assalamu alaikum, sir.